Okay, so last time we started talking about buffers, and we actually had an example. Okay, and we said that a solution that has a stable pH is what a buffer is. And so in the previous slide, we said that when you had that mixture, let me go back to that slide. That was 1 molar in HX and 1 molar in its conjugate base. We found that even if we contaminated it with HCl, okay, the pH hardly changed. Okay, the original pH was 7. It was still more or less 7 uh, after we contaminated it with the HCl. All right. So generally, you get a buffer anytime you have comparable and non-trace amounts. So it can't be a trace amount. There has to be comparable significant amounts of weak acid and its conjugate base, or a weak base and its conjugate acid. And when we say comparable amounts, you're looking at a ratio anywhere between 1:10 to 10:1. So if you take the ratio of the amount of base to the conjugate base to the amount of conjugate acid, anywhere from 0.1 to 10, if that ratio is there, is what you have, then you have a buffer. The best ratio is the best buffer you can make from that acid-base combination is a 1-to-1 ratio. Okay? So, and we did look at an example, compare that example we had earlier with just pure water that had a pH 7, where a single drop of HCl, the same amount of HCl added to it, caused the pH to drop from 7 to 3. Big jump if it was if you just have pure water. So if your solution is not buffered, it has a tendency to change pH drastically by just a little contamination with an acid or a base. Okay? So how do you calculate the pH of a buffer solution? The nice thing about buffer solutions is that when you mix, if you have a source of an acid, a weak acid, and a source of its conjugate base. So here's an example where you have 0.5 moles of acetic acid, and you mix it with half a mole of sodium acetate, and you make up a solution. The nice thing about buffer is that because you have comparable amounts of conjugate acid and base, okay, they tend to suppress each other's ionization. So for practical purpose, you say at equilibrium, provided there you have comparable amounts, at equilibrium, whatever starting amount you have is going to be the same. So for example, HX, what do we know about HX in water? It gives you H plus X minus, right? So if you start off with 0.5 moles of acetic acid let's say per liter, okay, then but you also have 0.5 moles per liter of X minus, okay, then this ionization is going to be suppressed because of the presence of the conjugate base. The same thing with the conjugate base. Its ionization in water, which will give you HX plus hydroxide. You can think of it this way. If you have 0.5 moles per liter of your base and 0.5 moles per liter of your acid, okay, the ionization of your base is suppressed by the presence of the acids. So pretty much whatever starting amounts you have at equilibrium, that will still be the same amounts if you can see that you've got comparable amounts. And now what did we say are comparable amounts? Anywhere between 0.1 and 10. Okay, so solve this problem is fairly simple. Okay, so you just say, okay, this is the actual concentration here is going to be 0.5 over whatever the volume is, right? Since you're given the mole, so you have to have concentration. So your equilibrium concentrations is going to be 0.5 over V for acetic acid, and for your acetate, sodium acetate, so this is the conjugate base, acetate, C2H3O2 negative, and acetic acid is HC2H3O2 negative, HC2H3O2, okay? So this is what we're referring to as HX here, and that's your X minus. So the concentration of your conjugate base is also 0.5 over total volume. And let's be more precise here. Let's put the right number of sig figs that are given in the question. All right. So what would be the concentration of H plus? You know that Ka is equal to H plus times X minus over HX, right? So you can say that's going to, you can solve for H plus if you're interested in the pH, correct? So how do we solve for H plus? Let's rearrange this. I can say that H plus equals Ka times Hx over x minus. Do we know what our Ka is? Our Ka is not given, but we're given the pKa. It's 4.74. So that is 10 to the negative pKa. Okay, so Ka would just be 10 to the negative pKa. And Hx is how much? I mean x minus is 0.5 moles over the volume. Okay. And your x minus concentration is also 0.5 moles divided by the volume. Okay. So it doesn't really matter what the volume is, right? It just cancels out. And so 0.5 over 0.5. That's 1. So this is just 1. So this is a 1:1 buffer, we say. The ratio of the conjugate base to acid is 1:1. So what's our Ka here? What is our H plus here? It's just 10 to the negative pKa, right? Since this is 1 times 1. So what's our H plus? What is our pH? pH would be log of 10 to the negative 4.74. It's just a negative log. It's just negative of negative, so it's positive 4.74. If the ratio is 1:1, pH will just be equal to pKa. If the ratio is 1:1. Okay? And you'll find that if the ratio is 10:1, okay, or 1:10, then your pH is either, it's going to be anywhere between pKa plus 1 or pKa negative 1. In other words, the useful range for a particular conjugate pair would be within 1 unit of its pKa. Okay? So that's what you'll find if you did that. Let's take a look. Let's look at another way. Let's look at this another way. Okay? If you have Ka equals H plus times x minus over Hx, then you can say, if you take the negative log of both sides, you can say negative log of Ka equals negative log of H plus, okay, plus negative log of base, which would be x minus over acid Hx. So I'm just taking the log of this, okay, this expression down here. But what is negative log of Ka? That's pKa. So that's equal to negative log of H plus, which is pH, minus log of base over acid. Okay? And so let's rearrange this to solve for pH. Then you can say pH equals pKa plus log of base over acid. This equation right here is a very, very useful equation for quick calculation of pH if you know the pKa and you know the base to acid ratio. Okay? So pKa here plus or minus the base to acid ratio. This is called the Henderson-hasselbalch equation. It's really this, just what's the word? Another way of writing your expression for Ka. So you really don't need to memorize this, but this just happens to be a convenient equation to use when we're dealing with buffer questions. Why? What happens if the ratio is 1? Then you can say pH equals pKa plus log of 1. What's log of 1? 0. So pH equals pKa. Okay? What happens if the ratio is 10? So what if x minus over hx is 10? Then your pH will be pKa plus log of 10. What's log of 10? 1. See? What happens if the ratio is 0.1? X minus over hx equals 0.1. Then your pH is going to be equal to pKa plus log of 0.1, which is going to be negative 1, right? So you would expect your pH then to be, okay, pKa minus 1. All right, so if you know the pKa of your weak acid, then the buffer that you can expect to make from that has to have a pH that's somewhere between pKa minus 1 and pKa plus 1 for it to be a good buffer. Okay? It works best that way. Okay. So what's the range of pH values for an acidic acid sodium acetate buffer if the pKa of acetic acid is 4.74? Well, if it's 4.74, that's 4.74 plus 1. 5.74, 4.74 minus 1 would be 3.74. So you can use acetic acid and sodium acetate as a buffer to make a buffer if the pH that you want to stabilize, the desired pH that you want is between 3.74 and 5.74. Okay? And the closer you are to 4.74, the better your buffer. Okay? Let me see. There's a couple of, something I forgot to mention in the slides I might encounter in the homework. What's the reason why, if you have a pair of conjugate acid and conjugate base, comparable amounts of it in a mixture, why does the buffer work? Why does it have a stable pH? The reason is this. Let's say you added an acid to this buffer, okay? I mean a base to this buffer. Well, you have an X minus, right? You have a weak base from the buffer, and this is your contaminant. What will happen? Well, X minus plus hydroxide, HX from the buffer. Okay, you have HX from the buffer. The weak acid from the buffer will neutralize any base that you add to it. So if you add a hydroxide, then the weak acid from the buffer will react with that hydroxide and will give you what? What's the product of these two reactions? It gives you water plus X minus, right? What happens if your contaminant is H plus? If you add an acid to your buffer, what will happen? Then the weak base that's in your buffer will react with H plus to give you HX. And what do we know about these two reactions? These have very large KEQ. Okay, so these reactions are almost essentially complete. So in other words, you can add hydroxide or H plus to your buffer. They will not, but total concentration of hydroxide and H plus will not significantly change because there is something in there that would convert that hydroxide into water, okay? And there's something that will convert the H plus into HX. So there is no significant effect on the pH of your solution. Remember, pH is negative log of H plus, right? So how do you make a buffer? One way is to mix reagents that will serve as a source for the conjugate acid-base pair. An example we just had earlier was acetic acid. HC2H3O2 is the conjugate acid. And when you do sodium acetate, NaC2H3O2, okay, your sodium acetate will give you acetate ions. That will be the source of your conjugate base. Okay, so how do you explain why a solution that's got comparable amounts of sodium carbonate and sodium bicarbonate works as a buffer? What acid does this give you? This breaks up in water to give you sodium ions and bicarbonate ions, right? What does this give you in water? Sodium ions and carbonate ions. Can you identify the two ions here that's a conjugate pair? This and that are a conjugate pair, right? So if you have significant amounts of bicarbonate and carbonate, then you can have a buffer. Okay, so that's one way you can make a buffer. You just mix a weak acid and the salt of the weak acid. Okay, so here's your weak acid and its salt, or you can mix two salts. Okay, as long as they have the anions are what do you call them? Are a conjugate pair. The two anions from the salts are a conjugate pair. Right? So let's try this question right here. Which of the following mixtures would not make a good buffer when dissolved in water? Examine this pair that we have here. Okay, let's see. How do we do? Okay, popular answer is C. Why C? This will give you H3PO4. What's the conjugate base of H3PO4? H2PO4 minus, right? So this doesn't give you H2PO4, this gives you HPO4. So this will not give you a good buffer. What about this one? You have HSO4 minus, so bisulfate and sulfate. That's a conjugate pair, so that's okay. H2PO4 and HPO4, that's a conjugate pair, so that's okay. So C is the correct answer. C is the one that's not going to give you a buffer. Okay? Good. Another way you can prepare a buffer is to partially neutralize a weak acid by a strong base. Okay, for example, acetic acid, you can half neutralize it with sodium hydroxide. What would be the pH of that solution? And why would that work? Well, let's say you have a weak acid, HX, right? If you have and you add sodium hydroxide to it, gives you what does this give you? HX plus hydroxide. That's a complete reaction because if you calculate the KEQ for this, it's going to be a big number. Weak acid plus strong base, pretty much a complete reaction. So that's going to give you X minus plus water. Okay? So if you start off, let's say, with 0.5 moles per liter of this, and you only add 0.25 moles per liter of sodium hydroxide. So let's just imagine that, okay? What would happen? What would be your changes? Reaction is going to go all the way, right? So which one's your limiting reactant? Sodium hydroxide. You're going to lose the 0.25 here. You're going to lose the 0.25 here, 0.25 over here. How much X minus will you make? 1-to-1 ratio, so 0.25. So at equilibrium, what will you have? You'd end up with 0.25 here, a trace amount here, and you have 0.25 here. Okay, so if it's half neutralized, what's the X minus to HX ratio in this case? If it's half neutralized, 0.25 over 0.25 is equal to 1. Okay, this is the Ka, by the way, not pKa. Make that correction. So what is the pH going to be? If the ratio is 1:1, pH is just going to be pKa, right? So pKa plus log of the ratio, which is 1. And what is pKa? Negative log of, so this is 0. Negative log of Ka, which is 1.8 times 10 to the negative 5. So that's going to be 4.74. I did that earlier. I gave you that pKa value earlier, right? correct? Now, another way you can make a buffer is you neutralize a weak base by a strong acid. For example, let's say you have a solution, ammonia solution, okay? Let's neutralize that by HCl, so that gives you H+. The HCl will give you the H+, so that will give you ammonium ions, okay? Again, let's just make up some pretend numbers here. It doesn't really matter what numbers we use. Let's say we have 1 molar of ammonia to begin with. Okay, so our initial concentration is 1. And let's say our H plus is, okay, if you're going to lose 40% of your ammonia, so you're going to lose 40%, right? Minus 0.4. How much H plus did you add then? 0.4. Because that 0.4 is going to be all pretty much gone. And how much ammonium will you make? Plus 0.4. Those would be your changes. Okay. So overall, at equilibrium, you would say you would end up with, instead of 1, you now have just 0.6 for the ammonia, right? 40% of it is gone. You have 0.6 left. And you have a trace amount of H+. How much ammonium would you make? Also 0.4. So what's our pH here? This is pKa plus log of, what's the base over the acid here? This is your base, right? And this is your acid. So how do I know ammonia is the base? It's a proton acceptor. So this is going to be 0.6 over 0.4. I just need to know what pKa is for ammonia. Actually, pKa for ammonium, right? How do I know pKa? This is pKa of the acid, so I need the pKa of ammonia. Well, you can look up. You'll find pKb of ammonia is 4.74, okay? Or you might find Kb of ammonia to be 1.8 times 10 to the negative 5. You can look that up. So how do I get pKa of ammonium? What do we know about Ka and Kb for a conjugate pair? For a conjugate pair, Ka times Kb is Kw, right? That means pKa plus pKb, just like pH and pOH, they add up to 14. So if I know pKb of ammonia is 4.74, how do I get the pKa of ammonium? I'm going to say pKa would be 14 minus pKb. Okay. And then I'll say that's 14 minus 4.74. So 14 minus 4.74 is how much? 9.26. So that's the pKa. So this is the pKa of ammonium ion. Right? So that's going to be my pH. That's what I plug in here. Okay. So this is, what was it? 9 point, how much? This is how much? 9.26. 9.26. And what's log of 0.6 over 0.4? 0.6 divided by 0.4, that's 1.5. Take the log of that. That's 0.176. So what's 9.26 plus 0.176? So that's 9.26. It's 9.43. Okay, that's the pH of your mixture. Now, let's see if this is reasonable. Okay, one way, that might help you out during tests is to see if numbers are reasonable. If the pKa is 9.26, okay, and you have more of the base, right? More base compared to acid. So you would expect your pH to be more towards the basic side of pKa, so higher than pKa. And in fact, 9.43 is higher than 9.26. Okay? So if you have more of the conjugate base, your pH would be higher than pKa. If you have more of the conjugate acid, your pH is going to be below pKa. If they're equal, then your pH is equal to pKa. Okay? So that's a good testing tip, like, especially if you're doing multiple choice and you're limited in time. That might be a way to eliminate some answers. All right. A few disclaimers about all the calculations we've been doing so far. Okay, some of the examples we've been doing are really simplified because in water, in aqueous solutions, there could be a lot of reactions going on. So you can have several equilibria. So you have several equilibrium conditions that need to be satisfied. For example, we talked about the solubility, the relationship between solubility and KSB. We've been ignoring the hydrolysis of ions. Okay, so for example, you may say like calcium carbonate. Okay, you have equilibrium between calcium and carbonate. But you do know that that carbonate can react with water to give you HCO3 minus plus OH minus, and so far when we've been doing KSP calculations, we've just ignored any hydrolysis. Okay. Now on your test, unless otherwise told, you can make that assumption. Just focus on the reaction that you're asked to look at. Okay. You can also have ion. You can actually do have ion pairing in solution. So for example, if you have a solution that contains magnesium and fluoride ions, you can have pairs of magnesium and fluoride. Okay. So the effective concentration, that would lower the effective concentration of magnesium and fluoride ions. And this other thing I mentioned earlier, that we said that we're using concentrations as activities, right? As our approximate values for activities. Okay, whenever you have a very high total concentration of ions, the activities of ions will become significantly less than the molar concentration. Okay, so that approximation activity equals the concentration is typically not very true, especially once you get to really high concentrations of ions. Okay, and the values that you find when you look them up from literature values, those are actually based on activities, not on concentration. All right. So there's a few more applications here. Here's one practical application in the lab of the concept of equilibrium. If you have an insoluble salt in the lab, okay, and you want to dissolve it, one way you could dissolve it is by trying to add acid to it instead. So if you can't get it to dissolve in water, one common technique you do in the lab is you add acid to it. It might dissolve, okay? And the explanation for that has to do with cases where if you have the negative ion of your salt, if the anion of your salt is a conjugate base of a weak acid, then that will have a greater tendency to dissolve. But if the anion is a conjugate base of a strong acid, adding an acid will not help in the dissolution of your salt. Okay? Let's illustrate that with silver phosphate. If you add acid to silver phosphate, you'll find that it is going to be soluble in the acid. So here's the expression for the dissolution of silver phosphate in water. Silver phosphate gives you 3 silver ions plus phosphate ions. What do you call the KEQ for this? Solid going to solutions. The KEQ for this is called the KSP of silver phosphate, right? And if you look up the KSP, you'll find that the PKSP is 16.05. So what is the KSP? If PKSP is 16.05, KSP is 10 to the negative 16.05. That's a very small number, right? 10 to the negative 16. But let's look at what happens to your phosphate. Your phosphate, okay, will react with H plus if you add an acid to your. So you have a silver phosphate solid right here, right, in a beaker, silver phosphate, and then you add HCl to that. So the HCl will provide the H plus, okay. What happens to H plus phosphate? It gives you HPO4 2 minus. What's the KEQ for that? HS plus PO4 3 minus gives you HPO4 2 minus. That's just the opposite of HPO4 2 minus giving you H plus HPO4 3 minus. The KEQ for this is 1 over K3. Okay, so the KEQ for this is 1 over the K3 of H3PO4. And if you look it up, K3 for H3PO4 is, I've looked it up for you already. K3 for H3PO4 is 12.35. Okay? So the KEQ for this would be 1 over 10 to the negative 12.35. Okay, K3 is 10 to the negative 12.35. You can look up K3 for H3PO4, you'll find it's 12.35. And then if you look at this second reaction right here, what is that? That's just the opposite of K2, the second ionization step. So this is 1 over, the KEQ for this is 1 over K2. So that's 1 over 10 to the negative 7.20. You look it up, you'll find the second step for the dissociation of ionization of phosphoric acid has a Ka of 7.2. And then finally, this H2PO4 minus can further react with H plus. We're assuming you're going to add enough acid here, so your H plus H2PO4 will give you your phosphoric acid. The KEQ for this is 1 over K1. So that's 1 over 10 to the negative 2.15. So 2.15, you can look that up as a K1 for phosphoric acid. So what's the overall KEQ? If you add up these 4 reactions, you end up with silver phosphate plus H plus gives you 3 silver ions plus H3PO4. What would you get there? For the overall reaction, your KEQ is equal to the product of these 4. So 10 to the negative 16.05 times 1 over 10 to the negative 12.35 times 1 over 10 to the negative 7.20 times 1 over 10 to the negative 2.15. Okay, so our KEQ is just going to be 10 to the negative 16.05 minus negative 12.35, so that's plus 12.35, minus negative 7.20, so that's plus 7.20, minus negative 2.15, so that's plus 2.15. And that gives you 16.05 negative plus 12.35 plus 7.2 plus 2.15. That gives you 5.65. 10 to the 5.65. And that should give you inverse log. So that's going to give you 4.46. Okay, or 4.5 times 10 to the 5th. That's a large KEQ. And so silver phosphate is soluble in acid. Now, if you actually do this in the lab, okay, you'll find that silver phosphate is a yellow solid. So if you add acid to it, it will dissolve. But one thing you'll realize is if you add HCl, okay, that yellow solid might dissolve, but it's going to be replaced by silver chloride, which is a white solid, a white precipitate. Okay, and the reason why you get silver chloride is insoluble in water. And silver chloride will not dissolve in acid. And the reason for that is why. If you have silver chloride, you try to dissolve it in acid, okay? That would give you Ag plus HCl. Well, what do we know about HCl? you can't make it in water. So the KEQ for this is going to be very small. In fact, the Ka for HCl, okay, is at least, Ka for HCl, it's a strong acid, is at least, estimates range from, vary, but it's at least 10 to the 6th. Okay, so that would make your KEQ for this process small enough that the silver chloride will not dissolve as a result of adding acid to it. So practical application in the lab, if we have, let's say, a mixture of phosphate and chloride, you can separate the phosphate from the chloride, okay, by precipitating both. Add silver nitrate to the solution. So you'll precipitate silver phosphate and silver chloride, and then you add some other acid, preferably not HCl, because HCl will add more chloride. But you can use HCl. You add HCl, that will dissolve the silver phosphate, and then your silver chloride will remain as a solid. And then what you do is you can separate your solution from your solid. Okay. You can also apply this to the cation. Instead of trying to convert the anion, you can convert the cation to dissolve something insoluble. So if you want to dissolve, for example, silver chloride, acid doesn't work, right? This is a low KEQ right here. KSP for this is 10 to the negative 9.745. So that's a small number. So what you can do, since you can't get silver chloride to dissolve in acid, what you can try to do is try to dissolve it in something else. You can try ammonia, because ammonia will react with silver ions to give you a silver amine complex. Okay, you look up the KF, formation constant for silver amine, it's 7.05. So this reaction right here, complex formation reaction between silver ions and ammonia, the KEQ for that is 10 to the 7.05. So if you combine these two reactions to get the overall reaction, the KEQ would be 10 to the negative 9.745 plus 7.05. That's going to be equal to 10 to the 9.745 negative plus 7.05. That's negative 2.695. Okay, that's somewhat small, but that's big enough to cause your silver chloride to dissolve. Okay, that's going to be what did I just do? Calculator stopped working. 2.695 negative. Change that to exponential notation. It doesn't know how to do. Okay, try again. 2.695 negative antilog equals, so that's that's equal to 0.002. Okay, so that's small, okay, but not very small. So it's actually big enough that silver chloride, if you add ammonia to it, depending on the concentration, you can actually get it to dissolve. 1 molar ammonia, for example, can get your typical silver chloride precipitate in the lab to dissolve. You compare that with silver iodide. You have basically the same solution, same process here. You're going to try to dissolve silver iodide in ammonia. In this case, your KEQ is going to be 10 to the negative 16.056. That's your KSP, multiplied by 10 to the 7.05. How much would that be? So 16.056 negative plus 7.05, that gives you negative 9. Okay, so your KEQ for silver iodide plus ammonia gives you 2 silver amine complex plus iodide. If you try to dissolve iodide in ammonia, it's not going to work because the KEQ for this That's 10 to the negative 9. So practical application of this in the lab, you have a mixture of chloride and iodide. You want to separate them. So you add silver nitrate to both of them. You'll get silver chloride and silver iodide. But if you want to separate them, you can add ammonia to your mixture. Your silver chloride will dissolve. Your silver iodide will remain as a solid. Okay, so this is selective dissolution by adding a complexing agent for the metal cation. Okay, so these are some practical applications of equilibrium in the lab. Okay, another practical application in the lab is in selective precipitation. And again, you'll notice these are all about controlling your reactions. That's the reason why we're interested in studying equilibrium. We want to be able to control reactions. We want to be able to have some reactions go and have some reactions not go, right? So let's say your solution is buffered at pH of 9. So you can make a buffer. So you have a reaction mixture, you buffer it to pH of 9. What would be a good buffer for that we've seen earlier? You remember? pKa of ammonium was like 9.26. So an ammonium chloride buffer would be something you might want to use for that. Okay, so your pH your solution is buffered at 9. Which cation, if present at a concentration of 0.01, will not precipitate? So let's say you have a mixture that has calcium ions and aluminum ions, and the concentration of either one is 0.01 molar. Okay? Let's say you want to separate the two. Can't you separate them by precipitating one but not the other? You can try precipitating one of these two but not the other. You can calculate that if that would happen at a pH of 9. So how do we do that? Well, what's the concentration of hydroxide H plus at pH 9? Let's do hydroxide since we're doing the hydroxides. Okay. So what's POH at 9? pH of 9. If I know my pH, what's my POH? 14 minus pH, right? So 14.000 minus 9.00. That gives me a POH of 5.00, right? So if my POH is 5, what's my hydroxide concentration? It's going to be 1.0 times 10 to the negative 5. Okay, let's review. How do we know if we're going to get a precipitate or not? We calculate the ion product and compare it to KSP, right? So what's Q for calcium hydroxide? So it's going to be calcium ions times hydroxide squared, right? So what's our calcium ion here? We're going to say it's 0.01, and our hydroxide is 1.0 times 10 to the negative 5th. Square that. So that gives you how much? It's 10 to the negative 10, and that's 10 to the negative 2, so that's 1.0 times 10 to the negative 12. How does that compare to KSP? What's the KSP of calcium hydroxide? 5 times 10 to the negative 6. Okay, so that's less than 5 times 10 to the negative 6. It's less than the KSP. So calcium hydroxide will not precipitate. You can do a similar calculation for aluminum hydroxide. And let's see if it will precipitate. So Q, the ion product for aluminum hydroxide, equals aluminum concentration times hydroxide concentration, but this time it's going to be cubed, right? Because you have 3 ions of hydroxide in your aluminum hydroxide. So again, aluminum concentration is 0.01 same as the calcium, and hydroxide is 1.0 times 10 to the negative 5, so you cube that, and what would that give you? That's 10 to the negative 15, and this is 10 to the negative 2, so that's 1.0 times 10 to the negative 17. How does that compare to the KSP of aluminum hydroxide? KSP of aluminum hydroxide is 3 times 10 to the negative 34. So compare that. Is that bigger or smaller? Much bigger, right? So it's much larger than the KSP, so this will precipitate. Q is greater than KSP. So that's another application in the lab of the idea of equilibrium. Okay? Okay, this might be a good time to pause.